A couple of announcements before we dive in. First of all, there are GCC student planners for the year 2013 to 2014. They are free of charge for you. You just have to go down to the advising center to pick one up. These are the ones that have specifically the GCC dates on it. You know, when is a Monday, a Wednesday, which days do we have no classes, all that stuff. They are free. They are quite nice. Anybody happen to have one on them right now from this year? Advising center is down on the second floor. Yeah. June, perfect. Yeah, so these are this is an old copy of the student planner, and it has a day-to-day thing that you fill in all your stuff on, but again, it's personalized to GCC. Okay, so go pick one up in the advising center. Also, we are in the middle of spring week, and there are spring week activities every day this week. In particular, today is game day. From 10 to 2 in the dining commons, you will find free food and free entertainment. There are going to be some large-scale games, chess, Connect 4, and Jenga, ping pong, air hockey. I will take any comers on foosball. I was quite good at foosball when I was a college student, so bring it on. So I'm going to head down at like noon today right after my other class, so check it out if you're interested. That's today. You are not allowed to spin them in foosball. It's a rule. What's that? There are, what I've heard, there's two ping pong tables there, and there are 2 members of the faculty who are quite good at ping pong, actually, who are both going to be down there. Are you good?
I'm all right, but I just want to like smash.
Yeah. So go down and play some ping pong. Okay. So the project is due today, but I do want to give a hint. So apparently, part 2 of the first problem here. What's the probability that you and your opponent split the next 2 points? I didn't mean for it to be tricky, but I have now added this hint that I will share with everybody here. There is more than one way to split the next 2 points. So I think that some people just wrote in here, okay, to split the next 2 points means I win the first point and they win the second point. And that's valid. But there's more than that way to split the next 2 points. So you need to incorporate something additional here. Maggie. Yeah. So if you want to find the probability of winning a tied game, so we assume we're tied right now, maybe you win the very next 2 points. You've already found that probability in part A. Maybe you split the next 2 points, but then win the next 2 after that. You found that in part C, I think. Or you could split the next 2 and then split the next 2 and then win the 2 after that. These are all different possibilities. So you've already found the first 3 probabilities that you want. And anytime you see the word or in probability, what operation does that mean? Add. So you're going to add a bunch of the answers that you've already found, plus, etc. All the answers you didn't find, but it could go forever. But the nice thing is that series that you get is a geometric series. So we can use the formula. Yeah. End of the day is fine. If you wanna tweak things, that's okay. Just win the game. That's all I want. Wait, what? Tied is yeah. As long as you start, that's all I'm saying. That's my way of saying started at 0-0. We could also say the game goes up to 2. That's it. Just yeah. Tiffany, did you have a question? Right. That's right. Yeah. Yeah. And is multiply or is add. And I think we saw that back a few days ago when we gave that hint about the gunfight at the OK Corral. Or sorry, it's the It's All Good Corral. Or was it here? Right. Remember we did this long calculation, and if you wanted to follow that yellow path, meaning miss and miss and miss and hit, we multiplied all the probabilities together. But separately, all the ways that A could win, you could win on the first shot, or you could miss and then win over here, or you could miss, and then win over here. And we ended up adding those or probabilities up. This is here in black. That's right. If you follow one branch, it's multiply. But then if you want to if you want to find all the branches at the end with any possibility accounted for, you add them up. That one I probably should have been more clear, but yes, that was the end of the game. Yeah. Yeah. No, we changed it to a paintball game. Okay, so what page are we on? 22? All right, we'll have a quick look at our calendar. Today, again, Project 7 is due. End of the day is fine without penalty. The quiz, again, is due first thing next class. Project 8 will be assigned next class. If you are ready to get started on it, you can pick one up. They're over there. But Project 8 has a lot to do with power series, so probably it won't make much sense if you pick it up today. So today we talk about our last tests for convergence. I think I still have up here. No, I don't. The big chart with which we've been looking at had all these tests for convergence in it, and the only two we haven't talked about yet are the last two: absolute convergence and the alternating series test. That's the topic for today. Any questions on the calendar? Mm-hmm.
What is the federal difference between test 3
The final will be comprehensive versus test 3, which will just be on this series stuff that we're working on. The final exam will be comprehensive. It will also include a question or two on this last week of material that we're going to talk about differential equations. The final exam is also, in theory, supposed to be easier is not the right word, but I feel okay asking kind of detail-oriented questions on the individual tests. But by the time we get to the final exam and we're in this cumulative thing, I'm not as nitpicky. At least I aim to not be as detailed. So it's really more big picture ideas that I'm trying to test on the final exam. Any other questions on the calendar? So right now we're about halfway through the material for test 3. Okay, so we've got a shortened class today, so we're just going to give kind of highlights for today. Let's jump down to, again, on page 22. We're going to take a look at number 4. It says, write out the first 5 terms of each series and determine whether or not each series converges. So let's begin with part A here. Okay, so this one has a funny -1 to the n plus 1, which maybe we haven't really seen before, so we're going to see the effect of that right now. When you plug in n equals 1, what's the power? It's 2, so -1 squared is +1, and it gets divided by the same n equals 1. So the first term is 1. Now we plug in n equals 2. What's the power? It's 3. So -1 cubed is really -1 divided by n is still 2, so it's -1/2. Okay, and then when n is 3, what do we get? +1/3 is good. When n is 3, that becomes a -1 to the 4th up there, which makes it +1. And the next term, maybe we can identify the pattern already. -1/4, one more term, +1/5. So even if we hadn't seen it before, we're now kind of identifying, oh, -1 to the n plus 1 is just going to make the thing flop back and forth between positives and negatives. Make sense? And so because this series alternates between positives and negatives, we call it an alternating series. All right, so that's the kind of series we're studying today, is series where they alternate between positives and negatives. You can see down here, -1 to the n. It's not exactly the same, but can you tell what the only difference is going to be for the -1 to the n versus -1 to the n plus 1? It's just going to start with a negative. Right? When you plug in n equals 1 down here, -1 to the 1 is a negative. whereas up here we started with a positive. But it's still going to alternate. So it makes really no difference what's up there. It's just determining whether you start positive or negative. Okay, if these terms were all positive, then what would the name of that purple series be? The harmonic series. And we know the harmonic series converges or diverges? Diverges. But this is an alternating series. So maybe, just maybe, there's enough cancellation happening there that it's going to converge. Do you buy that that's a possibility at least? The harmonic series with all pluses, it added up to infinity. But here it's not all pluses, so there's cancellation happening. And maybe there's enough cancellation that the thing doesn't blow up to infinity like it did before. So here's the basic idea with the alternating series test. I'm just going to draw a quick picture here. There'll be a 0 there and a 1 over here. Real number line, all the numbers between 0 and 1. So what is the first term in this purple series? Oh, so I can give a name to this guy. This is called the alternating harmonic. I would be willing to also call that the alternating harmonic, but I think technically it starts positive 1 for that name. Okay, so what's the first term in the alternating harmonic series? It's 1. So then I'm going to come over here. Do you guys remember we used S for the partial sums? S1 is the sum of the first term just by itself. The sum of the first 2 terms is what we called S2. How much is the sum of the first 2 terms? Is 1/2. So then we went, let's see, so we bounced over here to there to get to S1, and then S2, it turns out, is right there in the middle by going backwards 1/2. And then S3 is the sum of the first 3 terms. So let's see, that was 1/2 plus 1/3. How are we with our fractions? What is it? 5/6 is good. So we're going to bounce to the right, land on 5/6. I'll say it's about here. S3 is 5/6, and we're now bouncing this way. And the next term, I don't care about the final answer, but how far are we moving in which way? Moving 1/4 to the left. We buy it? Right. So the first term was the bottom green one. We went 1 to the right, and then we went 1/2 to the left. Now we're going 1/3 to the right. Next one is 1/4 to the left. And do you see that even if I don't know what the final answer is going to be, there's no chance this is going to be infinity, right? I mean, it's just honing in. The right answer, if I add those guys forever, is some number inside of here. It's just merging, you know, like it's not moving. It's always moving with a smaller step than the previous one. It always just goes back and forth. So this guy converges to some number between, you know, 1/2 and 5/6. There's no question. And basically that's the alternating series test. So let's look at the alternating series test details. So it says a series of the form -1 to the n plus 1 times a sub n, which is just a1 minus a2 plus a3 minus a4. It's just same as our generic series, but with pluses and minuses alternating. It converges if 2 things happen, and this is the alternating series test. First of all, we need this to be true. This says that the series is either increasing or decreasing. Forget the pluses and minuses. But what does this guy say? It says an plus 1 is smaller than an. Does that mean increasing or decreasing? That means decreasing. The sequence of terms is decreasing. So ignoring the minuses, it is true. Looking at, so it's kind of like absolute value. Technically, the way that this is written, the a sub n is the part that ignores the minuses already. So the a sub n, in the case of what we just did down here in purple, the a's are 1, 1/2, 1/3, 1/4. The minus signs are built in with that -1 part there. Yeah. So the terms here, ignoring the minuses, 1, a half, a third, a quarter. Do you buy they're decreasing? Of course, right? Ignore the minuses. Those guys are decreasing. And then the other condition that you need is that you need the terms themselves to go to 0. It's not enough to just be decreasing. They need to decrease to 0. Do we believe that to be true for 1, 1 half, 1/3, 1/4? Yes, they're headed to 0. And so the picture that we drew down here at the bottom, I copied a picture from your book. It's the same idea. You jump to the right a certain amount. So you go A1 to the right, but then you go a smaller number to the left, and you go an even smaller number to the right, and an even smaller number to the left, and the answer is definitely someplace in there. If you let it go forever, it's going to converge. So that's the conclusion. Alternating series test just says if you have an alternating series and ignoring the minuses, the terms are decreasing to 0, and the series converges. That's the alternating series test. So let's just write out the details of that test here. So here A sub n is everything except for that alternating part. So 1 over n. Just not writing down the -1 part. So let's check the limit as n goes to infinity of those terms themselves. What does this limit equal to? Equal to 0. That's one of the 2 conditions we need to check for the alternating series test. So the terms go to 0, and what else needs to be true about the terms? They need to be decreasing. So let's go ahead and compare the a sub n term with the a sub n plus 1 term, where instead of n, what are we putting? N plus 1. Everybody see these 2 things? This is a sub n plus 1, and this is a sub n. That's what we're supposed to compare. Again, ignoring the minuses. Yeah. Yes, I quite like that analogy. And it felt like you were almost describing a pendulum there, where it eventually kind of decays to nothing. Yeah, great. What inequality goes in between? Less or greater? Less, right? That's the second condition. I needed the next term to be smaller than the current term. So because of those 2 conditions, the original series, and I'm not going to say it, I'm going to copy it, converges by the alternating series test. Okay, any questions on the alternating series test? When do we use it? When we have an alternating series. It's pretty much a dead giveaway. If you have an alternating series, you're going to try the alternating series test. Okay, let's go back up and try number 2, which is the same idea, but here it's a -1 to the n over n squared. So let's just write out, say, the first 4 terms, maybe. When n is 1, -1. When n is 2 and when n is 3, go ahead and write out the next few terms. Yes. What's the next term? Plus 1/4. Next one? Minus 1/9, and then it continues. Okay, So it is an alternating series because it goes back and forth between pluses and minuses. To figure out whether or not this guy converges, you can use the alternating series test, and it's pretty straightforward to do so. We're not going to write out the details, but if you just look at the terms themselves, what's the formula for a sub n, ignoring the plus minus? Is 1 over n squared. Just ignoring that negative 1 to the n, just call it a 1. Okay, two conditions need to hold. The terms need to be decreasing. Are these terms getting smaller, ignoring the pluses and minuses? Definitely they're decreasing. And are they heading to 0 in the limit? They are. Alternating series test tells you that the series converges. But there's an even more basic reason that this series converges. Suppose that we didn't have the minuses. Suppose it was all plus. 1 plus, 1/4 plus, 1/9 plus, ... Do you know whether that series converges or diverges? 1 over n squared. This is a p series, right? And p in this case is 2. What's the magic cutoff for p series? 1. Is this the convergent or divergent side of 1? It's convergent. So that thing right there with all pluses is a convergent p series. Well, if I add the thing up with all the pluses and it's still finite, then what's going to happen when I have some cancellation by introducing some minuses throughout? It's going to be smaller. It's going to be more finite than the first one, right? So if you have something that converges and it's already all plus, and then you decide that some of these terms are really minus, well, it's the first one is the top one is definitely going to converge. And so that right there is this test here. If the series where you have absolute value around the terms converges, meaning if you make them all positive and it converges, then absolutely, if some of them are negative without the absolute value in here, then that series converges. Yes, exactly. The alternating series, these ones right here, if you add these guys up forever, it is definitely smaller than what you get when you add these guys forever, but adding these guys forever is finite. We already know that. So that right there is the easier way, the more basic way to show that this guy with the minuses converges. We didn't even need the minuses in there. It was already converging when it was all plus. Okay, so let's go to the next page. All right, we're going to skip past the error thing. You can read about that in the book. We're going to jump down here to number 7. Okay, in 7, it says, if you can make everything positive and it still converges, that's a very strong statement. And so we're going to say that that series right there, including the minuses maybe, is called absolutely convergent. If you can stick absolute values around it and it still converges, then the original series is absolutely convergent. Let's look at the two examples that we've already examined. These are the first two examples that we did. This guy was the alternating series test, sorry, the alternating harmonic series. And this is the one that we just saw a moment ago. When we put absolute value around this, that gave me the sum of 1 over n squared. Converge or diverge? Converged, which is a very strong thing. So what does that mean about the original series without the absolute value? It is called absolutely convergent. Absolutely convergent. So this series right here without the absolute value is absolutely convergent. Did the same thing happen with our alternating harmonic? If I take the absolute value, I get the sum of 1 over n, right? Converges or diverges. This one diverges. But the original series, the alternating harmonic, we showed that that converged. So yes, the alternating harmonic converges, but in some sense, it kind of only barely converges because if I decided to make all the terms positive, I lose it. It goes from convergent to divergent. We really need that cancellation to make the series convergent. So in that case, it's not absolutely convergent. We have another name for it. If the absolute value part diverges, that was our harmonic series, but the original thing, including all the minuses, converges, that's our alternating harmonic, then we say the original series is conditionally convergent. So this series circled here in red is conditionally convergent. Conditionally is kind of like on a trial basis or like outside of a math class, like you've seen condition, like on the condition that. So, you know, on the condition that you keep the minuses in there, you're okay. But if you decide to get rid of those minuses, it doesn't work. So that's called conditionally convergent. Okay, so last thing, this is just kind of a cute little example that will make your brains explode. So in number 9, it says if you regroup the terms in a finite series, then the sum is unchanged. So if we do 1 minus 2 plus 3 minus 4 plus 5, let's just get a number. What does that equal to? 3. Now I'm going to regroup the terms. 1 and 3 I'm going to group together. 5 and minus 2 I'm going to group together, and minus 4 is at the end. Just make sure that the minuses are still in front of the same numbers. It was negative 2 and negative 4. It still is. So without doing the work, you should believe that that's 3, right? You can check if you want to, but rearranging, of course, will make no difference. But unfortunately, that's not true for infinite series. Somehow, for some infinite series, rearranging the terms will actually change the sum, which is quite disturbing. So here's an example. The alternating harmonic series, we've already seen it. 1 minus 1/2 plus 1/3 plus minus 1/4, all the way down, right, forever. Okay, so here's what we're going to do. We're going to group this in a very strange way. All you have to do is verify that all the terms up there are copied in the next row. Okay, so the 1 goes here, the 1/3 goes here, the 1/5 goes here. You see the odd fractions are going to go first. Yep, and they're all positive. Then I'm going to skip to the ones that are multiples of 4. This minus 1/4 is here outside. The minus 1/8 is here outside. The minus 1/12 is outside. So all the multiples of 4 are there. But there are some other numbers that we haven't grabbed yet. These are the even ones that aren't multiples of 4, right? Like 1/2 and 1/6. So starting with a half, skip 4 ahead to a 1/6, skip 4 ahead to a 1/10. Those guys are minus, yes? So it's a very strange way to rearrange, but we can follow this pattern forever. 7, 9, and 11 would be then in the next ones. So 7 would be the next odd guy, right? 9 would be the next odd guy out here. Okay, how much is 1 minus a half? There's a half, that's there. A quarter is copied. 1/3 minus 1/6. See, so that's really 2/6 minus 1/6 is a 1/6. Minus 1/8 is there. 1/5 minus a 1/10 is a 1/10, right? Because that's 2/10. All right, so that's there. Minus a 1/12 is there. I'm going to factor a half out of all of these guys. Fair enough. So we get the 1, 2, 3, 4, 5, 6, etc. Yeah? This thing in here has a name. What is it? That's the alternating harmonic series, which is really disturbing because we started off with the alternating harmonic series equals 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 half of itself. Some really clever person was trying to come up with some way to blow our minds and figured out this. I mean, it's really strange, but it's very clever, this pattern that they found. So you say faster, but can you name a denominator which is a multiple of 4 that isn't going to be here somewhere?
Of course not, but it's like, since it's infinity, you're going to have a larger infinity on the one.
So we have to. There's a lot of strange stuff that happens with infinities, and I will tell you that the number of denominators that are multiple of 4 is the same as the ones that are even. That there are different levels of infinity, but there aren't any of those different levels of infinity here.
So you're saying that all the numbers other than the quarters versus the numbers that are the quarters are the same level?
Yes. In fact, I can say it even stronger. I can say the number of fractions in this list is the same as the number of fractions with the multiples of 4.
But so 3 times infinity equals infinity.
In some cases, it does.
So of course, the sum of the alternate series.
Yeah, but this is not infinity. If I add it up, it converges to some number. But what you're saying is 3 times infinity is infinity, and I agree with that in many cases. But well,
I'm saying because you're having 3 times infinity of 1/4.
Yeah.
Or of the regular ones, and then regular infinity of 1/4.
So maybe we can mess with the sum. Yeah, and we can. Yeah, David. I'm sorry that we've ruined infinity for you. Maggie. That you don't need to memorize this trick or this pattern. Yeah. I can't. I haven't seen this particular trick applied anyplace else, so I can't try to generalize this to something different. All I can say is that some clever person came up with a way to show that the alternating harmonic series is equal to half of itself, which is a very strange property to have. And then it turns out that by suitably, all right, so this is only true because we started with a conditionally convergent series. The alternating harmonic series is conditionally convergent. It converges, but just barely. We need that cancellation with the negatives in it. If it were an absolutely convergent series, I could not change the order of the terms and affect the sum. For absolutely convergent series, change the order of the terms, the sum is still the same. It still approaches whatever finite number it approached before. No, it doesn't diverge, but I guess what I'm saying is that if you add these guys up forever on an Excel spreadsheet, you'll get some decimal. I couldn't even tell you what the decimal is. But if you decide to add them up in this order, you will get a different decimal. It'll be half of what it was before. Yes, it's very strange. And worse than that, you can take any conditionally convergent series and you can make it add up to any number you want. So you can decide to make this thing add up to 3 or 4 or pi.
So does that mean there's no way to find the sum of
There's a way to find the sum of a conditionally convergent series, but changing the order in which you write the terms changes the sum. So
like, find something that's always itself?
yeah, I mean, if you pick a sum beforehand, I can rearrange these terms and put them in an order that will get you your sum. You could say anything, right? No, the only series that we're going to be expected to be able to find the sum of is a geometric, right? We haven't found any sums of actuals, any like actual answers in several classes. The answers we're getting now are converges or diverges. We can't say anything more. So no, I won't ask you to do that. But that's a good reason you gave. Mm-mm. It could be. You could have an alternating series which is geometric. Oh, was the one on the quiz geometric today? Oh yeah. Yeah, there's an alternating geometric on the quiz today, but the only reason we can find the sum is because it's geometric. It's really special. Yeah, good. Okay, so I know we just have a couple of minutes left. If you feel like working for those few minutes, you can start the group activity stuff here. And there are answers that follow down at the bottom. Oh.